Welcome everyone to this week's Autonomy Talk. This week is a great pleasure to have with us Professor Neda Masoud, who is an associate professor of civil and environmental engineering at the University of Michigan. Something about Neda: she holds a Bachelor of Science in Industrial Engineering and a Master of Science in Physics, and she then received a PhD in Civil and Environmental Engineering from the University of California, Irvine. And in her research group, she's dedicated to developing operational and planning tools that deal with the innovation of the next generation of mobility systems, in particular in their abilities to be connected, automated, electrified, and shared. Today, she's going to talk about a particular one of these issues, which is cybersecurity. And we are all very excited to hear more about it. And thank Neda for the improvised earlier talk than it was expected.
Thank you, Giola, for the introduction, and apologize everyone for our late start today. So as Giola introduced me, I'm an associate professor of CE at University of Michigan, and today I'm going to present our collaborative work on cybersecurity in connected and automated transportation systems. This work has been supported by CCAT, Center for Connected and Automated Transportation, Region 5 University Transportation Center. And I would like to also start by acknowledging other former students and former and current colleagues who have been collaborating with me on this work: Yi-Young Wang, Ruxian Zhang, Ethan Zhang, and Dr. Anahita Kojandi. So let's get to it. Connected and autonomous vehicles, we are gradually progressing toward the future transportation system that is both connected and automated. Maybe not at the pace that matches the ambitious timelines that were initially promised, but the evolution is steady and certainly promising. So in a CAV system, we anticipate a myriad of benefits from CAVs, at the forefront of which is safety. The U.S. Department of Transportation expects to see a decrease in fatal traffic crashes by 80% in a fully connected and automated system, mainly due to the reduction in human error. We expect to see extensive energy savings, anywhere from 3 to 20%, depending on how connectivity, autonomy, and specifically electrification are leveraged in future CAV systems. And finally, one of the benefits of CAVs is traffic stream stability, the benefits of which can manifest in many forms, including increasing road capacity, reducing congestion, increasing reliability of travel times, what have you. So there are a lot of benefits, but at the same time, when we delve into the intricacies of integrating CAVs into our existing systems, numerous challenges emerge. And today, I want to focus on one particular aspect, and that is cybersecurity or sensor faults and failures in CAV systems. We know that CAVs employ onboard sensors and communication channels to perceive the environment around them, to make informed decisions, and basically this subjects them to uncertainties in measurements. Now, these uncertainties could be in form of noise in the sensor systems, noise in the communication channel, time delay, message drops in the communication channel, and many other forms. At the same time, this increased levels of connectivity and automation indicates that CAVs have more attack surfaces compared to legacy vehicles. These attack surfaces could be internal services such as the OBD unit, any number of sensors on board vehicles such as LiDAR, or they could be external surfaces such as roadside units, the communication channels, so on and so forth. So in order to combat this challenge of uncertainty in measurements, we would like to design detectors, fault detectors in CAV systems. But at the same time, we have to pay attention to the fact that CAVs have access to constrained resources. In general, we envision CAVs to be electrified, and basically the only source of energy they have is the battery in the vehicle. And this battery has to be utilized for a variety of purposes, ranging from perceiving the environment, processing data, making decisions, and propelling the vehicle. And so given these constrained resources that we have, we want to devise fault detectors that are computationally light, and we don't want to burden the CAV any further with its storage limitations. All right, so before I get into the meat of the presentation, I would like to address two fundamental questions. So in reality, anomaly detection in general and cybersecurity in particular are multidisciplinary fields that involve various expertise and skills. Historically, we've had professionals from several fields, ranging from computer science to forensic science to psychology, contributing to solving cybersecurity problems. And specifically for decades, computer scientists have been focusing on threat detection and monitoring in cyber physical systems. Now, when you think about it, connected and automated vehicle systems are also cyber physical systems, even though they are new. But they are cyber physical systems at the end of the day. So this begs the question, can we simply adopt existing threat monitoring systems and apply them to CAV systems? Or do CAV systems have unique characteristics that necessitate further exploration of solutions in the cybersecurity space? Also, another question is, can transportation engineering knowledge help facilitate the detection of cyber attacks? And on the other side of the coin, how can cybersecurity affect transportation as a system? I would like to think that the answer to those questions is yes, and I present the work I'll be presenting today, I hope will convince you as well. So the transportation system can provide context for movement of vehicles, and this context facilitates detection and identification of cyber attacks. And on the other side of the coin, the efficacy of cybersecurity solutions that we devise could impact the degree to which the anticipated benefits of CAV systems can be realized in transportation systems. All right. So an anomaly detection scheme could introduce two types of errors, false negatives and false positives. A false negative is when a detector fails to identify an anomaly as an anomaly. So what happens is that a true anomaly goes undetected and falsified data enters our decision-making process, and it is easy to see that why this could have severe, potentially fatal consequences. On the other hand, we have false positives. A false positive is where the detector erroneously identifies an anomaly, basically erroneously identifies an actual event in the network as an anomaly. And basically disregards that event from the decision-making process. And although it might not seem as such, this type of error could also have consequences that are just as severe as the previous type of error we talked about, the false negatives. So to elaborate on this further, consider a situation where an actual event in the network has led to an abrupt and unexpected change in the pattern in which we're observing data, in the pattern of observed data, basically. So this could be, for example, an unexpected braking from a downstream vehicle. If the vehicle, the CAV, falsely detects such an unexpected change as a fault or attack and disregards this information, this might lead to the CAV not reacting to that event in a timely manner and could have potential negative consequences. So in order to prevent this type of false positive error, it is necessary for vehicles to incorporate network level information into their anomaly detection schemes to help explain some of these seemingly unexpected changes in the pattern of observed data and prevent them from being detected as anomalies. So we are in the business of designing fault detectors, and we want our fault detectors to have a specific properties. One is, the first one is that we want them to be able to account for context, which I elaborated on in the previous slide. We also would like them to be able to address noise. This noise could be introduced through the sensor network or through the communication channel, and the noise the problems that are created by noise are typically exacerbated due to time delays in receiving information. We would like our detectors to be able to address missing values in our data streams as well. So these missing values could arise from sensor failures or message drops in the communication channel, or even due to attacks such as jamming attacks. And finally, I talked about the fact that CAVs have very limited computational resources, so we would like our detectors to be lightweight. Okay, so given this background, here is the agenda for my talk today. We talked about the fact that we want to incorporate context into our detectors to help reduce the rate of false positive errors. So we are going to do that first for a simple scenario by integrating a car following model into a fault detector. Then we are going to make it a little more complex and integrate a platooning model into our fault detectors. So when it comes to platooning, there are a lot of benefits that we expect from platoons, including increased road capacity. But at the same time, these benefits could only be realized if we are dealing with stable platoons. So after designing a detector that can incorporate a platooning model in it, we would like to analyze the string stability of vehicular platoons under potential cyber attacks. So let's get started with the first item on the agenda. So the objective of this study is to detect sensor anomalies and recover the corrupt signal by utilizing the leading vehicle's information. And so we want to do that by incorporating, as I previously mentioned, a car following model. So this is our subject vehicle, and this is the leading vehicle. And we would like to use a car following model that can basically capture the interactions between these two vehicles and inform our fault detector. Now, we make a few assumptions. First, we assume that vehicles move according to a car following model. We assume that vehicles have access to location and velocity of their leader, and this access could be obtained through sensors that are on board the subject vehicle or through the communication channel. Vehicles can control their acceleration. And finally, we assume that there is a known time delay tau that captures any time delay present in the system, ranging from communication time delay, sensing, and actuation delays. Later, we discuss how this time delay actually doesn't have to be deterministic and can be stochastic. Okay. All right, so for our anomaly detection method, we are going to adopt a Kalman filter paired with a fault detector. For those of you who might not be familiar with a Kalman filter, a Kalman filter is a recursive algorithm that estimates the state of a dynamic system from a series of noisy measurements. So it basically has two steps, a prediction step and an update step.
No problem. There's somebody which is unmuted, and I will ask to. Okay, I think that's solved now.
Okay, good. So in the prediction step of the Kalman filter, this step involves predicting the current state of the system based on the previous state and the known dynamics of the system. So this is just a very simple description. Typically, there are more intricacies involved. And in the update step, the predicted state is updated using the actual measurement. The Kalman filter weighs the predicted state and the measurement based on the respective uncertainties to produce a more accurate estimate of the current state of the system. So, so within as I mentioned, Kalman filter is a recursive procedure, and so we keep applying the basically mechanisms that I talked about iteratively with time. So a byproduct of this is what is called I'm sorry, I'm blanking. So a byproduct of our Kalman filter will be utilized to inform a fault detector. We investigate two different types of fault detectors. One is a statistical method, and the other one is a learning-based method. And we'll get to the details of all of this in the next few slides. All right. Okay, so let's first introduce our car following model and then see how we can use this car following model to form a state transition or a motion model in our Kalman filter. So over here is the setting we are working with. We have a vehicle, the subject vehicle, indexed as n, and the leading vehicle is indexed as n-1. The distance gap between vehicles is d, and the difference between the speed of two vehicles is basically d dot. And car following model basically gives us a control rule that specifies the acceleration of the subject vehicle over here. And this will be a function of typically a nonlinear function of the speed and speed of the subject vehicle, the speed of the leading vehicle, and also the difference in their speed and the spacing between them. Now, you notice that we have a t minus tau here, which indicates that all of this information is being, so the decisions we are making is based on information that we are receiving 1,000 seconds ago. So there is some time delay involved in this decision-making process. So what we want to do is to incorporate this car following model into our Kalman filter, specifically into the state transition model of our Kalman filter. And so in order to do that, we form a state vector, which is a tuple with xn, the location of the vehicle, and vn, the speed of the vehicle, and also an input vector, which again is a tuple, including the location of the leading vehicle and the speed of the leading vehicle. And so with that, the control rule can be written down as a function of the state vector and the input vector, but at time t minus tau. So there is again a time delay present here. So with that, we can write down our continuous state transition model as follows. S dot can be written down as basically the derivative of the state vector. The first component is going to be x dot, which is the velocity, and the second component is v dot, which is the acceleration, basically our control law. Now, what you notice here is that our state transition model is a function of t, but over here we have our control law is a function of t minus tau. Basically what this indicates is that we cannot use this state transition model in its current form, because in order for us to use Kalman filter, we have to respect the assumption that our state transition model has to be Markovian based. All right, so in order to deal with this issue, we are going to have an approximation. And this approximation is based on an assumption of bounded acceleration. We know that vehicle acceleration is practically bounded, let's say between a mean and a max. And therefore, the change in the speed of the vehicle is upper bounded from above by a max times tau, and lower bounded from below by a mean times tau. Now, given this, we can rewrite the state transition model as such. So if you see here, the first component is the speed at time t. We can write it down as a speed at time t minus tau, plus the change in acceleration within the interval t minus tau all the way to t. And so the approximation that we use here is that we assume that this integral is equal to 0. And this will definitely have implications that we have to deal with later, but this is the assumption that we make at the moment. And this results result in us having to deal with a delay differential equation, but at the end of the day, now we can use a Kalman filter. So with that, our continuous time state transition model with discrete time measurement is presented in the following. As you saw in the previous slide, we have a state vector that represents the internal state of the system. We have a state transition model over here, which is a set of equations that describe the evolution of the system over time. And we have our measurement model, which is a set of equations that link the state of the system to the measurements that we have here. We also have a process noise over here. This process noise captures two things. First, it captures any bias that we introduce in our approximation step, where we approximated the integral of acceleration to be 0. And it is also able to capture any approximation that enters the equation as a result of assuming a specific car following model. We also introduce an observation noise here. All right, so as I mentioned before, so far we've been talking about time delay tau, but it is easy to prove that we can actually incorporate the stochastic time delay tau s by adding a random variable, zero mean Gaussian distributed random variable with a known variance, kappa, to the value of tau s. So this is based on the assumption that the leading vehicle's trajectory obeys a linear model with the acceleration of the leading vehicle following a Gaussian process with zero mean and, again, a different known variance. Under these circumstances, a random time delay of tau s can be shown to be equivalent to adding noise into the input vector un. All right, if you want to look at the proof is pretty simple, but if you want to look at the proof, you can refer to this paper. All right, so now we have our Kalman filter, but as I mentioned before, during the iterations of Kalman filter, there is a byproduct called the innovation that we can utilize to basically build our detector, fault detector. So what is innovation? Innovation is the difference between a state estimation and the measurement. Here we introduce a statistics called chi-square statistics that is typically paired with a Kalman filter. And this chi-square statistics can be utilized to basically detect anomalies. So this test, the chi-square test, defines the gate region and determines whether the new innovation falls into the gate region with a probability determined by sigma here, a gate threshold. So what happens here is that in order for us to use the chi-square detector, basically the way this test is built is based on assumptions that the data point we are using here, in this case innovation, follows a zero mean Gaussian distribution, which is not the case in our scenario for two reasons. First, because we might have an imperfect car following model, as I specified before, but secondly, because of the non-zero mean process noise that is introduced as a result of approximating this guy to be 0. Now, this guy could actually be 0 if time delay is equal to 0, if you don't have any time delay. So the system dynamics become much simplified if we don't have to deal with time delay, or under the circumstances where basically the acceleration and decelerations over this time period cancel each other out, which is, again, not something that we can count on. So innovation ends up not following a zero mean Gaussian distribution. In fact, if we draw innovation for a simple case, we see that it is far from a zero mean Gaussian distribution. So on the horizontal axis, we are looking at the innovation of location. On the vertical axis, innovation of a speed. If you recall, location and speed build our state vector. And the circle we are looking at here gives us the boundary of the chi-square detector. So if you look at the boundary, its center is at 0, 0, but the center of our innovation is somewhere around here, and you see that the innovation is not Gaussian distributed. So the typical detector, the chi-square detector that is typically paired with a Kalman filter, isn't really sufficient here. So we are going to use a learning-based method called one-class support vector machines. Support vector machines basically are try to give us the most generalizable decision boundaries in a binary classification problem. Now, in case of one-class SVMs, we train them using data that is 100% normal, so there is no abnormal or faulty data in our training set, but we make an assumption that a specific percentage of the data points are false positives. So given those circumstances, the one-class SVM tries to find the most generalizable decision boundary. All right, so how do we utilize one-class SVM? We are going to train a number of one-class SVM models, specifically M, with different probabilities. Recall that these probabilities are the rates of false positives. And then we are going to when we are using our Kalman filter, we are going to calculate the average innovation within the previous capital N time epochs. And then we adaptively, based on the value of this average innovation, decide which of these detectors, one-class SVM detectors, we want to apply. So the idea is the smaller our average innovation, we want to select the one-class SVM model with a larger P. Positive rate or sensitivity rate. The reason for it is when the innovation is small, the Kalman filter is basically doing a pretty good job in detecting anomalies, and as a result, we want to make sure in predicting the dynamics of the system, and as a result, we want to make sure that any small deviation from that is captured as an anomaly. All right. So without getting into details, I just want to give you a very brief overview of how the general framework works. So at each time epoch, the following vehicle receives measurements from the leading vehicle and also collects sensor data from its own onboard sensors. Then our Kalman filter, and so let me be a little more specific here. We talk about a specific form of Kalman filter. It is an adaptive extended Kalman filter. Adaptive is due to the fact that we will update the parameters of our Kalman filter as time evolves and the characteristics of the system change. Specifically, we update the covariance matrices of the measurement noise and the process noise. And extended basically means that the motion model or the state transition model we are utilizing is nonlinear. So within this framework, again, we start by smoothing the following vehicle's signal. So the speed and location based on the motion model that we have. So this is our state prediction. Then the Kalman filter generates the innovation, which again measures the discrepancy between the measurement and the prediction, and sends the innovation to the fault detector for anomaly detection. Our one-class SVM fault detector consists of several models and it dynamically chooses which one to use based on the average innovation it is receiving. If there is no sensor anomaly detected, the innovation will be combined with the measurement to generate an estimation of a state. And otherwise, we do not trust the current sensor measurement and we replace the estimation with the prediction, which will be used in the next time epoch. So just a very brief description. Now we want to do a series of experiments, and so I want to just spend a few minutes talking about different anomaly types that we can introduce for the sake of our experiment. So we are using, following literature, we are using 4 simple anomaly types that could be added to readings from any type of sensor. First, we have the short anomaly type. This is a single sharp and abrupt change in the observed data between 2 successive sensor readings. Then we have noise. Noise is an increase in the variance of the sensor readings, and it is different from the short anomaly type because the noise anomaly type occurs around multiple successive sensor readings. Then we have bias. Apparent from its name, it's a temporary constant offset from the sensor readings. And finally, we have gradual drift, which is a small and gradual drift in the observed data using basically within a few consecutive time periods. All right. So how do we use these anomaly types in our experiments to generate a data set? So we start with an actual trajectory that is collected by a connected vehicle, and we start injecting anomalies. We assume that the onset of anomalous values in sensors occur independently of each other. That is, we do not explicitly train our one-class SVM models on a data set that contains interdependent sensor failures or systemic cyber attacks on vehicle sensors. However, this assumption that the onset of attacks are independent of each other, it doesn't mean that we cannot have overlapping attacks. We could have attacks that multiple attacks during the same time period. All right, so let's get to our case study. So when I presented Kalman filter and we integrated a car following model to form the state transition model of our Kalman filter, we were pretty generic. We didn't specify the form of the car following model. But here in this case study, we actually have to specify a certain which certain car following model we are utilizing, and we are adopting the intelligent driver model, or IDM for short. We make an assumption that the input vector, that is the information we are receiving from the leading vehicle, is non-anomalous. So this is an assumption that may look like a strong assumption in the beginning, but it really isn't. When it happens that both the sensors aboard the subject vehicle and the leading vehicle's information contain anomalous data, as long as the deviation of the state prediction and the measurement exceeds the threshold of the fault detector, the system will still be able to detect sensor anomalies. However, when this deviation is not evident enough, it is not large enough, then under very rare circumstances, when the attacker manipulates both the input vector and the measurement such that they remain consistent according to our car following model, then the fault detector will fail to detect those anomalies. However, as you see, these circumstances are very hard to come by, because it would require knowledge from the part of the attacker on both the exact motion model that we are using, as well as the fault detector threshold, which, by the way, is dynamically being updated. All right. So the data that we receive comes from the safety pilot model deployment. So during this pilot, somewhere around 2,500 vehicles in the Ann Arbor area were equipped with equipment that could measure basic safety messages, and this data was stored. So we have a ton of data, and we use the mechanism I introduced in the previous slide to introduce anomalies. So we first extract in-vehicle speed for the leading vehicle. We then add Gaussian white noise to the in-vehicle speed of the leading vehicle, and this could also incorporate a stochastic time delay. Then we derive the location of the leading vehicle and the speed and location of the follower based on our car following model. And we introduce a random term to the speed of the following vehicle to induce state uncertainty. This figure shows you basically the type of data we are working with. So on the horizontal axis, we have time. On the top figure, on the vertical axis, we have the speed of the leading vehicle, which is our raw data out of the safety pilot data set, and the following vehicle, which is basically produced based on the car following model. And then in the bottom figure, we are looking at the distance between the two vehicles. Okay, so let's take a look at some results. We basically, compared to a very basic Kalman filter, we are making two contributions. First, we are using the IDM car following model to form the state transition model of our Kalman filter. And we are also replacing the chi-square detector, which is typically used with a Kalman filter with a one-class SVM detector. So we want to isolate and look at the impact of each of these modifications individually. So first and over here, when you look at the rows of this table, you see a parameter CI changing. CI basically is a value that tells us which specific anomalies we are applying. So CI would mean different things for different types of anomalies, but in general, as the value of CI increases, attacks become more subtle. So first we start with a case where time delay is equal to 0. And as you can imagine, we do our best. Our detector does its best, shows its best performance under this scenario. All right, so here is the case where we are using the chi-square detector without the IDM model and chi-square detector with the IDM car following model. And you can see that you can see that you see the area under the curve of the ROC curve, which is what we are showing in this table, is increasing, meaning that the detector is performing better. The next thing we want to look at is the impact of the fault detector itself. So chi-square detector, whereas the one class SVM, and you'll see that one class SVM is basically outperforming chi-square detector because if you recall, we were violating some of the assumptions of the chi-square detector, whereas one class SVM is a learning-based model and doesn't make quite assumptions that are quite as strong. Next, we want to see what happens when we increase time delay. So we are increasing time delay from 0 to 0.5 seconds to 1.5 seconds here. So let's just randomly pick one entry from each of these three tables and take a look. So as you can imagine, and this conclusion stands across all entries, as you can imagine, as we increase the value of time delay, the performance of our detector deteriorates because if you recall, the term we are approximating is a function of our time delay. So the approximation becomes more extreme and the performance of our detector deteriorates as we increase time delay. So this was pretty much the first study where we incorporate the car following model. I wanted to, before we move on to the platooning model, I wanted to just give you an idea of an alternative model. So if you recall, in the previous formulation, we had an integral that we approximated to be 0. In this different alternative approach, we form instead an augmented state Kalman filter, where the augmented state has a third term, and that third term is the integral itself that we approximated to be 0 previously. So this delta, which is the third term, we assume that this delta is a constant or a random variable with a small variance, and we assume that this time its derivative is approximated by 0. So previously we assumed that the term itself is 0. Now we approximate its derivative to be 0. And so we can repeat the same exercise, start with the original state transition model, and then form this new model based on this augmented state formulation. So the reason I'm introducing this is because in the platooning model that I'll present next, we are going to use this augmented state formulation. So this augmented state formulation is pretty much doing better compared to the previous approximation we had. So the figure on the left shows you the scatter plot of innovation sequence with the old approximation, and the figure on the right is showing us the scatter plot with this augmented state formulation. And you'll see that we are doing much better in terms of satisfying the requirements of the chi-square detector, although we are not 100% satisfying those requirements, but we are doing better in terms of zeroing basically the average of innovations and staying within the boundaries of the chi-square detector. So if you want to learn more about this alternative formulation, you can refer to this paper. All right. So with that out of the way, let's move on to the second item in our agenda, which is looking at the vehicular platoon. Up to this point, the quote-unquote context that we provided for our detector was through modeling the interaction between the subject vehicle and its immediate leading vehicle through utilizing a car following model. Now we want to extend this to a platoon of vehicles. What is a platoon? A platoon is basically a convoy of vehicles that, owing to constant communication between them, they can travel with steady speeds and with steady gaps between them, and they can offer a myriad of benefits, including increasing capacity on roadways, reducing congestion, what have you. So here, we assume that the subject vehicle can receive information from multiple platoon members. And more specifically, we utilize an M predecessor following information flow topology. Basically, we are assuming that the subject vehicle will receive information from M vehicles preceding it. This is an example of a tree predecessor following information flow topology. So this subject vehicle is receiving information from 3 vehicles in front of it. Okay. So now we would like to design a fault detector for vehicles within a platoon. And here is the set of assumptions we utilize. So first, we assume that the longitudinal dynamics of CAVs follows a platooning model. We assume that all platoon members follow an M predecessor following information flow topology. Here we consider 2 different time delays, stochastic time delays. One, tau 1, for the onboard measurements, so basically to measure time delay in the sensor systems, and tau 2 measures the delay in the communication channel, from the communication channel. And also, again, we have the bounded acceleration of each vehicle assumption. Okay, so I don't want to spend a lot of time on this because conceptually incorporating a platooning model into our Kalman filter, it's very similar to what we did with the call-following model. It's just mathematically more involved and notationally messier. But just to give you a very broad sense, the platooning model, it is a function of the velocity of the ego vehicle or the subject vehicle, the weighted sum of clearance gaps between the subject vehicle and the vehicles in front of it. And it is a weighted sum, basically indicating that as vehicles are farther away, the information they provide is less valuable and therefore receives a smaller weight. And also the weighted sum of relative velocities of vehicles. Now, just like before, we want to have a filtering and detection scheme. We form our state space model. Our state vector is the augmented state vector I showed you in the alternative formulation. We have our input vector. Input vector is a function of the average clearance gap and the average of relative velocities. And it's also a function of tau 1 and tau 2, the time delay in the sensor system and the time delay in the communication channel. So we use this platooning model to form our continuous time state transition model with discrete time measurement. And we use an augmented state extended Kalman filter paired with a 1-class SVM for anomaly detection. So that is all I'm gonna talk about in terms of anomaly detection. But more importantly, I want to talk about string stability in a vehicle platoon, because eventually, if vehicle platoons are not string stable, a lot of the benefits that we anticipate from them won't be realized in real world. So what is a string stability? A platoon is called head-to-tail string stable if any perturbations that cause the first vehicle in the platoon, that is the platoon head, to deviate from its equilibrium state can be attenuated at the very last vehicle, that is the platoon tail. Basically, what we do is that we take our platoon as a system where the input to this system is perturbation at the platoon head and the output is the perturbation at the platoon tail. So this input-output relationship between the platoon head and any other vehicle following it can be established by truncating the platoon at the corresponding vehicle. So this is a pretty nice, basically, feature because this allows us to describe vehicle responses in complicated longitudinal dynamics, where a vehicle takes outputs of multiple preceding vehicles and its output also serves as inputs of other vehicles. One last thing that I want to mention here is that string stability can be mathematically defined in both time domain and frequency domain. In time domain, it is easy to verify string stability, but it's pretty difficult to derive it. So we are going to try to derive head-to-tail string stability in the frequency domain. Okay. So we are talking about deriving head-to-tail string stability in a platoon of vehicles, but this is under ideal situations where there is no attack. So let's see how it can get done. So in order to derive head-to-tail string stability, we calculate the system transfer function. Basically, the Laplace transformation of the state space model will give us this system transfer function. So the system transfer function looks something like this. T is the transfer function. This is the transfer matrix. P hat is the transfer matrix, and you can see that its elements include a bunch of 0 and 1s and a bunch of transfer functions. So when you look at one element of this matrix, the index you see in the subscript basically tells you that this is a transfer function between vehicle n and vehicle n-1, n-2 over here. So once we define this transfer matrix, it is pretty easy to see whether we have a head-to-tail string stability or not. So we look at the largest eigenvalue of this transfer matrix, and if it is less than 0 under any frequency, then it shows that the platoon is head-to-tail string stable. All right. So head-to-tail string stability is defined for a system with a deterministic dynamic model. However, what happens is that when we are in a scenario where there could be cyber attacks, we are not working with a deterministic platoon dynamics model anymore. We are working with a probabilistic vehicle dynamics model. So in the scenario where there could be cyber attacks, we employ the detector we just talked about. And when we employ this detector, the detection sensitivity is not always 100%. So this indicates that there will be uncertainty in the platooning model that we utilize. So let us assume that all the vehicles in the platoon are equipped with the same detector with the detection sensitivity of P. We define a Bernoulli variable, eta here, and we assume that eta is equal to 1 if the system is completely uncompromised, and it's equal to 0 if the system is compromised. To decide whether a system is compromised or not, we take a very conservative approach. We assume that if one vehicle in a platoon is attacked, all vehicles are being attacked. So the only circumstances under which we can be certain that we are not compromised is when all vehicles can detect an attack. And that could happen with probability p to the power n if we have n vehicles in our platoon. We call this p tilde. And then the probability that eta is equal to 0, that is system is compromised, becomes 1 minus p tilde. So now we have the probability p tilde of having an uncompromised platoon and the probability 1 minus p tilde of having a compromised platoon. So under these circumstances, a probabilistic platoon dynamic model can be defined as such. So if the system is uncompromised, we use the same old dynamic model that we had before. But if the system is compromised, now we have to use a different model, a different dynamic model. All right. So now we are working under potential cyber attacks. We are working with a probabilistic platoon dynamic model. But a string stability that we looked at before, it is only defined for deterministic platoon dynamic models, not for deterministic ones. So how can we extend the string stability analysis to the case where we are working with a probabilistic platoon dynamic model? This brings us to the notion of pseudo-string stability. So we define a pseudo-string stability as follows. Consider a vehicle string with a semi-finite length in the equilibrium state. Impose a transient perturbation on the head vehicle of the platoon. The vehicle string is said to be pseudo-string stable if the perturbation eventually vanishes when reaching the tail vehicle in the string. Now, let me bring back the definition of a string stability under ideal circumstances where there is no attack, and make a comparison between the two. The one obvious difference between them is that pseudo-string stability is defined for a case where we have a probabilistic dynamic model, whereas a string stability is defined for a deterministic dynamic model. Another difference is that pseudo-string stability is defined for a case where our platoon length is infinite, but a string stability is defined for a platoon of vehicle of any size. All right. So now that we have a notion of pseudo-string stability, let's see how we can actually measure it, how we can mathematically determine if a platoon of vehicles potentially under attack is string stable or not. And this happens by utilizing the transfer matrix of the probabilistic platooning model. So we take this transfer matrix and look at its expectation under different values of p tilde. So to elaborate on this, so basically this expectation can be written down as p tilde, the probability that the system is not compromised, times the transfer matrix of the uncompromised dynamic model plus 1 minus p tilde times the transfer matrix of the compromised dynamic model. And now notice that the transfer matrix of a compromised dynamic model is a function of lambda, and this lambda is basically a vector of attack parameters. These attack parameters could be a tilde, b tilde, and c tilde. So these three basically capture potential attacks. If you recall, our platooning model composed of 3 terms. So these capture changes in the first term, second term, and third term respectively. And then tau 1 and tau 2 can help model potential jamming attacks on the sensor network and the communication channel. So we can further write this down in the form that is familiar to us. We saw in the previous slide by writing down these transfer matrices. So to define this mathematically, the pseudo-string stability can be verified as such. We define this transfer matrix, and again we look at the largest eigenvalue of this transfer matrix, and if it is less than 1, then we know that we have a platoon that is pseudo-string stable. Okay, so let's set of experiments. So let's go through the experimental settings first. We assume we have a 10 vehicle platoon in a ring road. Here again, we need to specify a specific platooning model. So we are going to use a model called cooperative IDM, cooperative intelligent driving model, for modeling our platoon dynamics. We assume all vehicles are initialized at the steady state with equilibrium clearance gap and velocity. And for information topology, we assume a tree predecessor following flow information. And we assume our tau 1 and tau 2 are equal to each other and equal to 0.5 seconds. We introduced a mixed set of anomaly types with an anomaly rate of 10%, and we assume that each individual vehicle is equipped with a detector and is able to recover the true state only if it successfully detects an anomaly. Now, with that, let me first show you some results on the efficacy of our detector, basically our detection performance. Now, in this set of experiments, we are on the ring road. We have 10 vehicles, but anomalies are injected only on vehicles 1 through 6. Now, on the top figures, we are actually looking at the velocity of vehicles and the spacing error of vehicles. Vehicles 0 through 9 are 10 vehicles under the scenario where there is an attack. Now, the spacing error here basically measures the difference between actual spacing and equilibrium spacing. So ideally, we want this to be 0, but because vehicles are under attack, it's not 0. And for the velocity in a platoon, we want all vehicles in a platoon to have the same velocity, but as a result of attacks, they don't have the same velocity. So the two figures at the bottom are showing you the same velocity and spacing error matrix, but after a detector is applied. So you see that the velocities of the vehicles are pretty much the same, and the spacing error is converging to 0, which bodes well for the detector we have. Okay. Next, if we want to look at head-to-tail string stability in this specific scenario. So if you recall, I mentioned that in the time domain, it is easy to verify a string stability, but hard to derive. So we derived conditions for head-to-tail string stability in the frequency domain, but we actually can easily verify whether a platoon is a string stable or not in the time domain, and this is what we are doing here. So basically, to verify this, we want to make sure that as we go down the platoon, the maximum spacing error over time for each vehicle is decreasing. So we are attacking vehicles 1 through 6. This is the case, figure on the top is the case where we don't have a detector. We are not utilizing a detector. So over the course of the experiment, the first vehicle, the maximum spacing error of the first vehicle is about 8 meters. For the second vehicle, it is increasing. For the third vehicle, decreasing, increasing again. So because we don't see a strict reduction in the maximum spacing error, we don't have a string stability here. But after we applying the detector, you'll see that the maximum spacing error is going down, indicating that we in fact do have a string stability here. All right, finally, one big question, one important question that we want to be able to answer out of all of this analysis is this: can a platoon be pseudo-string stable given a detection sensitivity P and a set of attack parameters captured in this vector lambda? So in other words, what is P star? What is the threshold of detection sensitivity? What is the minimum detection sensitivity that we can have such that our platoon remains pseudo-string stable? All right. So in this figure, I'm showing showing you the results. Basically, here. Here we are looking at, so on the horizontal axis, we have P tilde. So basically, we are increasing the sensitivity. And on the vertical axis, we are looking at the largest eigenvalue of the transfer matrix. As we discussed before, we would like this to be less than 1. And only when this is less than 1 is when we have a pseudo-string stable platoon. So as we increase the detection sensitivity, we are actually starting to do better and better. And it is at a certain detection sensitivity of P equal 0.985 in this case is where the magnitude of the largest eigenvalue falls under 1, and we start having a pseudo-string stable platoon. All right. One last set of experimental results. So over here, we are assuming that our 3 attack parameters, A, B, and C tilde, are equal to 0. And we assume that attacks are only occurring basically in form of jamming attacks, in the form of tau1, increase in tau1, the sensor time delay, and increase in tau2, the communication time delay. Now, the results here are interesting. So if you look at this, when we change the sensor time, before I get into the figure, in the vertical axis, we are looking at the optimal, basically, P tilde value. And so when you don't see anything, a curve here, this basically means that you could get away with having no detector at all and still maintain pseudo-string stability. Whereas in this region, in this graph, the probability is very close to 1, meaning that you have to have a perfect detector to maintain pseudo-string stability. So what we see here is that with sensor time delay, When the sensor time delay is less than somewhere around 1.5 seconds or so, we still can have pseudo-string stability regardless of how large the communication delay is. And on the other hand, after let's say 5 seconds of delay in the sensor time delay, we end up having to have a perfect detector in order to remain pseudo-string stable. But the trends for the communication time delay are somewhat different. So with the communication time delay, there is always a certain sensor time delay that could indicate you have to have a perfect detector in order to maintain pseudo-string string stability. So the takeaway from this is that pseudo-string stability is much more sensitive to time delay in the sensor network compared to the time delay in the communication channel. Now, there are a ton of more experiments that we have done, which basically target other attack parameters. And if you're interested, you can refer to this paper to look at the results. But I'm going to pretty much stop in the interest of time here. Just a quick summary. So here, what we've done in the space of cybersecurity for CAVs, and we've talked about today, is devising detectors by incorporating context into CAV anomaly detection schemes using car following and platooning models. We introduced time delay factors which introduce complexities that have to be taken care of. We employed learning-based methods, and we showed that they outperform statistical methods in the presence of imperfect models and approximations. We introduced the concept of pseudo-string stability when the state transition model becomes a probabilistic one in the presence of cyber attacks. And we finally demonstrated how a critical detection rate can be obtained to ensure pseudo-string stability of a platoon. So here's a collection of our work on cybersecurity. The first 3 papers are the ones I used for this presentation, but yeah, you're welcome to look at other works if you're interested. And this concludes my presentation, and I'm happy to take any questions you might have.
Thank you, Neda, for the great talk. So let's open the stage for questions. You can either write in the chat and I can read the question for you, or you can raise your hand and directly ask.
Hello, Neda.
Hi.
Hi, it's really nice to learn about your research. And my question is that in your case study, you consider to prevent cyber attack in like highway traffic, like car following model, and also in a platoon scenario. And I was wondering like how things can change when we consider such problem in a more complex traffic scenario like urban intersection. I mean, there could be several cars involved from different directions, and I'm wondering how the model can adapt to that scenario.
Yeah, that's a very good question. So the scenarios we're considering are pretty simple, right? So we only look at the car following model, which only accounts for one vehicle ahead of the subject vehicle, and then the platooning model where we consider multiple vehicles. You're absolutely right that in an urban environment, so first of all, there are other maneuvers that vehicles can do, for example, lane changing, merging, so on and so forth, that could, if we obtain and integrate models for those maneuvers into our system dynamics, we can definitely do better. And in an urban environment, it becomes even more complex with, as you mentioned, with the introduction of vehicles that are moving in the opposite direction and also other road agents. And this is definitely a topic that is of very high interest to me. But this is not something that we have worked on previously. But I look forward, this is a topic that I look forward to work on in the future. In terms of how current models can be adopted, there is no straight way in which they could be adopted. Conceptually speaking, we could have models similar to the car following model that could, capture the dynamics between vehicles in other circumstances, for example, in lane changing scenarios or merging, diverging scenarios, and incorporate them. But it is only at a conceptual step. The intricacies that goes into modeling them is not something that I have looked into.
Yeah, thank you for your answer. I'm looking forward to your further research into it.
Thank you. I appreciate that.
All right. Any other question for Neda? So I think I had one related to the second case study you were showing on the ring road.
Yes.
Actually, here is there any influence on your results from the fact that you're considering a ring road, like the fact that the flow influences itself over and over again, right?
Yes, exactly. So that is the reason we decided to use a ring road, to make sure that the first vehicle is also being impacted by other, so it's within it cannot just move forward, using a free flow speed. So are there effects that can be, just entangled in terms of is the effect we see on a certain vehicle a result of the experiment being operated on a ring road or not? I'm not sure about. So the only reason we use the ring road is, again, to make sure that all vehicles have something in front of them, right? So we have done experiments, similar experiments on just a straight, let's say, one lane highway road, and the results look pretty similar. So I tend to say that there is no specific complication or outcome that we can see as a result of doing the experiments on the ring road, but I haven't really looked too closely into it. But that's a great question.
Okay, thank you very much. No, those are interesting results. Any other question for Neda? I think you left your email in the last slide if people want to reach out for.
Yes, definitely. So this is our webpage, lab webpage, and my email is here, and I'm happy to connect with you.
Perfect. Thank you very much. It doesn't seem there are other questions, but I thank you again for the great talk, and I look forward to seeing some more results in this area.
Yeah, thank you, Jill, and my apologies again for
no problem.
Up that time.
You were super reactive. Thank you very much for giving the talk.
Thank you. I appreciate everyone for attending.
All right, and enjoy your day.
Thank you.
Neda. Thank you for the talk.
Bye.